Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Part 29, Decision Tree Regression and Classification. Now that we know the basic terminology of decision trees and we know what are the decision tree criteria, let's talk about the details of regression and classification models. In part 28, we talked about the basics and decision tree criteria. It's going to be a prereq for this class, so if you haven't watched that video yet, please make sure you watch episode 28 and then come back to this part 29. Starting with regression trees. So we're going to work on an example which is called baseball salary, and I borrowed this example from Introduction to Statistical Learning in R textbook. So this is a main textbook for many introductory level courses in machine learning. So in this example, the baseball salary is color coded, okay, and from low, basically blue greenish dots, to high, yellow and red. So look at that, we have two features, x1, x2, and guys, remember, this is regression, so it means that the target variable is continuous, right? And that target variable is baseball salary. In order to visualize it better, we're going to use colors to look at the quantities for baseball salary. So blue greenish ones are the lower salaries and the yellow reddish ones are higher salaries, right? So with that in mind, let's see if we can build a decision tree regressor here. So as a reminder, what are decision trees? Decision trees apply a top-down approach to the data, trying to group and label observations that are similar. So the key term is that basically you're going to label the data based on their similarities, right? Okay, so the main questions in every decision-making process in a decision tree are what? Number one, which feature to start with? Number two, where to put the split? Where is the cutoff point? I want you to pause the video and stare at this data set, at this graph here, and think about what feature should you start with? Should you start with years or the number of hits? Okay, so maybe you say, okay, it seems that if I start with the number of hits, it really doesn't matter where I put the split. If I put the split here or here or here, it seems that the colors are all around the place. So maybe hit is not the best feature to start with. So maybe you say, okay, let's start with years, right? If you want to start with years, so let's say, okay, years is going to be a better feature to start with. Where do you put the split? Maybe around 5, right? 4 something, 5. So anything to the left, again, you're visually satisfied, but we know that what is decision tree criterion for regression, right? If you watch the previous video, we look at MSE or RSS. And then we calculate the RSS after each split and we add them together, we compare those numbers, right? So it seems that here the dots are more similar to each other. So maybe we are satisfied with region number 1. What about region number 2? Not necessarily, right? Because there are blues down here and reddish ones up there. So maybe we need to do further splitting, right? Then I want you to focus on region number 2 and tell me what feature should we start with, years or hits? There you go, hits, right? So where you put the split, maybe somewhere around 100. Now you can say that, okay, it seems that observations in region 3 are more or less close to each other in terms of color, region number 2 and region number 1. We can go further down the tree, but just for the sake of argument, let's stop here and then try to interpret that, right? So, and this is what we're going to do. But before interpreting things, let's talk about the prediction of the model. Guys, remember, we have the decision tree regression divided the data, the entire train set into 3 parts, right? So R1, R2, R3. In each part, there are some values for baseball salary, and we know that they are more or less closer to each other, right? So we can take the average of all those values. Let's call them y bar 1. And then this is the average for y bar 2, and this is the average for y bar 3. So at the end of the day, this decision tree model is going to give you 3 numbers. So let's say you started with a 3, and then so maybe we ended up with 3 numbers, right? So this is maybe y bar 1, y bar 2, y bar 3. So this is a regression model. It means that if you want to try to predict baseball salary for an observation in a test set, let's use purple. If your players here with these amounts of years of experience and number of hits, your model is going to predict the salary is going to be y bar 3. If it is here, the model is going to predict the average salary is going to be y bar 2, and etc. Okay, so the predictions are going to be the 3 numbers here, actually. Only 3 numbers for prediction if we stop the tree here. Okay, now let's look into the interpretation. Okay, interpreting the results. So based on color-coded salary, it seems that years is the most important factor in determining salary. So we started with years, right? It was most important because we were satisfied visually for now with the split, right? With the colors, homogeneity of the colors. Later on, we're going to talk about how we can quantify them. For less experienced players, so if you're in the left-hand side, for less experienced players, the number of hits seems irrelevant. It really doesn't matter if you're hitting 150 or you're hitting 50. So there, it seems that the baseball salary, look at the colors, are very close to each other. However, among more experienced players, so if you are to the right side of this cut, the players with more hits tend to have higher salaries, right? So look at that. If you're on the right side of this split, this cutoff, it seems that the one that have higher hits numbers are getting more salaries compared to the one with lower number of hits, right? And it makes intuitively sense, right? So, and as you can see, the model is very easy to display and also easy to interpret and explain. So this is a big advantage of decision tree models. They are very, very interpretable, and we like that interpretability. So let's talk about the tree building process. So the steps are like this. Divide the feature space into j distinct and non-overlapping regions. So remember, we started with making the first split. We have region 1, region 2. They were non-overlapping, right? And then we ended up with 3 regions in that example. For every observation that falls into region Rj, we make the same prediction, which is simply the average of the target values, right, for the train observation. So let's look at that. So imagine we have region 1, 2, 3, and the prediction for region 3, let's call it y hat in region 3, is going to be one number, the average values for region 3. Predictions for y hat region 2 is going to be one number, and etc. Y hat R1 is going to be y bar 1. Okay, we are going to end up with 3 numbers. The goal is to find the regions such that the RSS is minimized, right? The residual sum of square. How do we calculate the residual sum of square? In regression, it's very straightforward, right? Basically, find the residuals and square them, y minus y hats, right? So y minus y hats to the power of 2 for each region, and we sum over the regions, okay? So for region number 1, we come up with RSS1, region number 3, RSS3, and region number 2, RSS2, right? So if down the process we are here, we can calculate the summation of these RSS, right? RSS, let's say the J goes from 1 to 3 in this example, right? So at each point at the tree, we're going to calculate. So based on the number of splits that we have, we're going to calculate this summation, right? And we're going to continue the process of cutting or making splits down the road, down the tree, as long as this summation is being reduced, right? So remember, you start with no split. If this is the entire data set, there's no split. You have RSS, residual sum of square. Basically, that's the deviations from the average, right? So that's residual sum of square, the average model. Basically, the RSS is going to be max. Then you make the first split. So you have one RSS here, one RSS there. You add them together. If this summation is smaller than the previous RSS, you say, okay, I accept this split, I go down the tree. And then down the road, you make another split. If the new summation, let's call it RSS3, if the new summation of RSS 1 through 3 is smaller than the previous summation, you're going to say, okay, accept this the split and continue, right? So we're going to go down the tree as long as this RSS is going to be reduced, right? If you look at the train set, that's going to be the case always, right? So intuitively think about it. If you simply just divide the data into more subspaces, the RSS is going to become smaller and smaller and smaller in the train set. So we know that if you don't put a stopping criteria for a decision tree, it's going to overfit at the end of the day. And we can make this, RSS, basically the summation, equal to 0. If you make a very bushy tree, and at the end of the day, each observation is going to end up at a one terminal node, so there's going to be no error, right? So the predicted value is going to be exact number that we see. So we already know that there's no point of tuning the model by looking at the train set. So that's why we have to look at the test set and make a decision that should we go down the tree or not. Okay, so now let's see how we formally define this tree building process. Okay, how does the algorithm select the feature xj and split the cutoff s? Okay, so the idea is very simple. We know that it is computationally almost infeasible to consider every possible partition of the feature space into J boxes. So for that reason, we're going to take a top-down greedy approach that is also known as recursive binary splitting, right? So it is top-down because it begins at the top of the tree and then sequentially split the predictor space, right? The feature space. And each split is indicated by 2 new branches further down on the tree, right? So that's why we call it its top-down. It is greedy because at each step of the tree building process, the best split is made at that particular step. Instead of looking ahead and picking a split that will lead to a better tree maybe down the road, right? So let's see how we can write it down. Xj and S are selected such that splitting the feature space into region, let's say Rj, R1 and R2, leads to the largest possible reduction in RSS. So this is what we discussed in the previous slide. So we are going to find these two parameters, Xj, Xj what feature to start with, where to put the split, by looking at which cutoff, which split, is going to reduce the RSS most, right? So here, let's say for the first cutoff, we have 2 regions, region 1, region 2. Then we can calculate where should we put this exact cutoff by going over this optimization problem, right? So in region 1, we're going to calculate the RSS. In region 2, we're going to calculate the RSS. So we end up with RSS1, RSS2. Then we try to minimize that, right? So we're going to change the cutoff. For example, we can move it from left to right and recalculate a new RSS1 and RSS2. And we'll see which one is larger, right? And we're going to pick this smaller one. So in this case, it seems that based on the color-coded observations here, it seems that the blue one, so the RSS1 plus RSS2, is going to be way smaller than the red ones, RSS1 plus RSS2. Okay, so again, in this simple example, it seems that this is a better cutoff compared to this, right? So this is going to be done iteratively, and the algorithm is going to be able to optimize basically what feature to start with and where to put the split, basically J and S. And we said that this recursive binary splitting is greedy because it doesn't look ahead and it doesn't look at the potential good splits down the road, right? So the best split is made at that particular step rather than looking ahead and picking a split that will lead to a better tree in some future step. So this is a caveat. This is a caveat of this model, and we are going to fix that one. Okay, we found the first split, and then what? Then the algorithm repeats the process, looking for the best features and a split in order to split the data further. And it does that to minimize the RSS within each of the resulting regions. Remember, the goal is to minimize the summation of those RSS, right? The process continues until a stopping criterion is reached, because without a stopping criterion, the model is going to overfit, right? It's going to go down the tree in the train set, and we know that the RSS is going to reduce, right? So we have to put a stopping criteria. For instance, that stopping criteria can be, okay, continue until no region contains more than a fixed number of observation, or continue to this level of the tree, to this number of depth, right? So in our previous example, let's say we have a stopping criteria, and that's going to be level is equal to 2, right? So stop that when the level is 2, do not split the data further. If that's the case, so here what we have. So we have the first feature to start with was years. If the year is less than 4.5, if yes, we go to the left. So yes here. We take the average of these observations, the average is 5.11, and we report this number as a prediction for every test set that you're going to see. You're going to predict here, right? So if you throw a test set into this decision tree, any observation in the test set that has the years less than 4.5 is going to be the baseball salary is going to be assigned to 5.11. If so, no goes to the right. Then if no, we need to make another split. Another split is based on number of hits. If number of hits is less than 117, so we are here. So we'll take the average of these numbers. So average is 6. So report this number for the prediction for all the new observations that you want to make prediction for. And then if no, we are here. Take the average of all these dots. It's going to be 6.74. And that's the predicted value for the test set in this region. Let's say these ones. All right. So now let's look at the 5-region example of recursive binary splitting. So the idea is that, depending on what's the stopping criteria, we can come up with more values for predictions, right? More terminal nodes. So in this example, let's say we have x1 and x2, and these are the cuts. So starting from, let's say this is cut number 1, cut number 2, number 3, and then number 4. And this is a decision tree related to that, corresponding to that box. So, and we are going to end up with 5 regions, right? So R1, R2, R3, R4, R5. We can visualize it in a 3D graph as well. So let's say we have x1 and x2 as features, and this is our target variable, and these are the level of predictions, right? So for example, let's actually go down the tree on one of these paths. So let's say if we can find region 4 in this 3D graph. Starting from the top of the tree, right? Is x1 less than t1? So the yes goes to left, no goes to right, right? So where's t1? This is t1. Is it less than t1? So the answer is no. So let's go to the right. Is it less than t2? So here is the value for, let's say, t2. Yeah, sorry, t is it t? This is t3. Yeah, less than t3. Well, no. Then is it? Then we look at. So basically, we are here. We are here now. Then the next cutoff is going to be is x2 less than t4. So if the answer is yes, we are in R5. Sorry, if the answer is yes, we are in R4. If the answer is no, we are in R5, right? So if you want to show it in this 3D plot, this is going to be our R4. R4. Okay, and then this number here is going to be the cutoff for our T4. Okay, so as an exercise, I want you to try to label all these numbers here. Okay, these are the average numbers. So we're going to get how many? 1, 2, 3, 4, 5 predictions for the model. Okay, we're almost done with the discussion of regression trees, but before going over classification tree details, I want to talk about the concepts of why decision trees in general are susceptible to overfitting in the train set, right? So let's look at the RSS in decision tree if there is no stopping criteria. So if there is no stopping criteria, this we can basically make this tree very bushy. So let's say it's a super bushy tree, and at the end of the day, imagine at each terminal node there's only one observation, right? If there's only one observation at each terminal node, so what is the prediction? The prediction is going to be equal to the value of that observation. So what do you think at each region, at each terminal node? What is RSS? 0, right? Because there's no error. So if we sum over all these RSS over the regions, over all the terminal nodes, so what do we get? 0. So as you can see, if we do not put any stopping criteria, this RSS can be exactly equal to 0. However, if we compare this one with a linear regression model, let's say a very basic model, here we have two features, x1 and x2, so let's write it down like this. There's a bias term plus w1 x1 plus w2 x2 plus some error term, right? Then, so how does it look like? Maybe it's a hyperplane surface like this, right? Something like this, and this is going to be the predictions, right? So as you can see, by construction, this linear regression model, the RSS can, maybe it can converge towards 0, but it's never 0, right? So in general, linear regression models are going to be less prone to overfitting compared to classification, to decision tree regression, right? So we have to be careful when it comes to tuning the hyperparameters. We need to make sure that we put a stopping criteria for decision trees. Otherwise, it's going to overfit. Now let's talk about classification trees. So we started this lecture by going over an example for classification, and we're going to stick to the same example, so we should be pretty much familiar with this graph here and the corresponding tree. Okay, so classification trees are very similar to regression trees, except that it is used to predict the qualitative response variable rather than a quantitative one. The other difference is that the decision tree criterion is different. For regression, we use RSS or MSE. For classification, we know that we are going to use entropy or Gini. Okay, and so the predictions of the algorithm at each terminal node would be the category with the maximum majority votes, right? So, or most commonly occurring classes. We saw the example that we are going to assign probabilities, and we say that, okay, in region 1, the class is going to take the highest probability or the majority vote. So R1 is going to be blue. We call the blues males, and etc. R2, again, male. R3, female. All right. Now let's see how can we calculate this decision tree criteria, this impurity measures. In part 28, I talked about the concept of Gini, Shannon entropy, classification error rate in more details, but I promised you that we're going to go over a numerical example to calculate the numbers. So let's go over that numerical example here. Okay. So we already know that classification error rate is not as sensitive to impurity compared to cross entropy and Gini, and we saw it by looking at this graph. Okay, so we said, okay, so it seems that entropy here, this is cross entropy, a scale version of Shannon entropy, is more sensitive to Gini, and Gini is more sensitive to misclassification error. Okay, and here are the formulas for them. So classification error rate, so this is nothing new. We have seen that it's 1 minus accuracy. Okay. Then for Gini index, we looked at this formula, the other version of that, but this is pretty much the same. It's probability of, let's say probability of mk multiplied 1 minus probability of mk. What is probability of mk? That's represent the proportion of the training observations in the mth region from the kth class. Okay. And then finally, cross entropy is the natural log version of the Shannon entropy, right? So Shannon entropy, this log is to the base of 2. But cross entropy is to the base of E. Okay, so I think going over a numerical example is going to be a lot easier to follow this notation. So let's, without further ado, let's look at that numerical example. So here is our simple example. Imagine there are two features, x1, x2, and we have two classes. There's going to be 10 red circles and 20 blue circles. Okay. We are going to calculate the Gini index, cross entropy, and error rate before making any split and after making a couple of splits and comparing these numbers. So let's start with the case that the entire training data set is used before making any split. Okay, so let's look at this one. This is the entire training set before any split. Let's calculate the error rate, the cross entropy, and Gini. Starting with the, let's start with the, well, actually, let's do calculate some probabilities first. So in this example, in this box here, what is the probability of blue? We have 20 blue and 10 red, so it's going to be 20 divided by 30. What is the probability of red? It's going to be 10 divided by 30. So with that, let's calculate these in measures. Okay, starting with Gini, maybe. So starting with Gini is 1 minus the summation of those probabilities to the power of 2. So 1 minus 1/3 to the power of 2 plus 2/3 to the power of 2. We're going to come up with this number, 0.44. For cross entropy, minus the summation of p log of p, right? So again, when the class is red versus when the class is blue, the probabilities. So 10/3 log of 10/3 plus 20, when I say 10/3, I mean 10 over 30, right? 1/3. And 2/3 log of 2/3. Okay, so if we add these up and multiply to -1, we get this number, 0.64. And finally, the error rate is 1 max the probabilities, 1 minus max of probabilities. So 1 minus the maximum of 10th, 30th, and 20/30th. So we get 0.33. I think we don't need to necessarily think complicatedly about this error rate. Look at that. So if you're classifying the class to be, I don't know, blue, what is the error rate? It's going to be 1/3. Okay. All right. Now let's make a split. The first split is going to be if the first feature to start with, let's say, just for the sake of argument, is x1 and the cutoff is s. Okay, so here's our cutoff point, and we are starting with x1. So we will end up with two regions. So region number 1, region number 2. Okay, at each region we can calculate probabilities. So in region number 2 we're going to have 9 blue and 1 red. In region number 1 we're going to have 11 blues and 9 reds. Okay, so what are the probabilities? The probability for blue in region 1 is going to be, let me use, probability of blue in region 1. This is our MK, right? P of MK. P hat of MK is going to be called 11 by 20, and probability of red in region 1 is going to be equal to 9 over 20. On the right hand side, the probability of blue in region 2 is going to be 9/10, and the probability of red in region 2 is going to be 1/10. Now with these four numbers, we're going to calculate the Gini, entropy, and error rate. So starting with Gini again, and so let me calculate one more thing. So overall, what is the probability of region 1? So how many observations we have? We have 20 observations, right? And out of, so here we have 10 observations. So 20 out of 30th, so 2/3, there's 2/3 probability of region 1 and 1/3 probability of region 2. Okay, so 2/3, look at the Gini, 2/3 for region 1, 1/3 for region 2. So 2/3 multiply 1 minus what? So we have, what are the probabilities in region 1? There are 9/20th and 11/20th, right? So 9/20th for red, 11/20th for blue. 1/10 in the region 2, 1/10 for red, 9/10 for blue. So if you do the math, you're going to see the number is going to be, the Gini with this split is going to be 0.39. We can calculate the cross entropy for this split. Exactly the same story. 2/3 probability of region 1, 1/3 probability of region 2, and within each region we can deal with their own probabilities. So if you do the math, we're going to get 0.57, and same story for misclassification error rate. 2/3 multiply 9/20th and 1/3 multiply 1/10. So we're going to come up with 0.333. Okay. So now I want you to compare these numbers. When we go from no splits to, let's say, split number 1. Okay, split 1. This is one choice, right? And look at that. The Gini goes from 0.44 to 0.39. The cross entropy goes for 0.64 to 0.57. And the error rate goes from 0.333 to 0.333. So not surprisingly, it seems that error rate is not that sensitive to change, right? Impurities, right? So for that reason, we're gonna, most of the time in practice, we're gonna skip this error rate. Okay? However, when you look at Gini and entropy, so it seems that there's a good amount of reduction in the impurity measures, right? So for Gini, we go from 44% to 39%, so there's 6% decrease here, 5% decrease here, right? For the cross entropy, we go from 0.64 to 0.57, so there is 0.7 decrease. Okay, so which one is more sensitive? The cross entropy is more sensitive, right? Now let's look at another split. So I leave this one as an exercise. So I want you to go ahead and do the same thing like what I did. Define them like R1, R2, write down the probabilities of blue and red, write down the probabilities of region 1 versus region 2, and try to calculate these numbers. Just confirm these splits, right? We're going to end up with this split. Well, this number for Gini, this number for cross entropy, and this number for error rate. Okay. Now let's say we have a split number 1 and a split number 2. So this is a split number 2. Split number 1 is that starting with x1 and putting the cutoff point as s. Split number 2, start with x2 and put the cutoff point for s, right? Then you want to see which one is reducing, which one is giving you the most information gain, which one is reducing the impurity measure most, right? So we have to calculate two other numbers. This one goes from 0.44 to 0.37. So what do we get? We get 0.07. And what is the difference between these two? Going from 0.64 to 0.54, so it's 0.10. And then this one goes from 0.333 to 0.3, so we are going to end up with 0.33. Okay. So which one is the winner? Well, again, cross entropy is going to be more sensitive to impurity, but between split 1 and split 2, which one is the winner? The one that reduced the impurity measures more, right? So the answer is split number 2. Why? Because this is the amount of information gain for Gini, which is higher than 5. For cross entropy, it's 10% versus 7, and for error rate is this number versus almost 0, right? So overall, the winner, so what is the takeaway from this slide? The winner between split 1 and 2 is going to be split 2, and cross entropy is going to be the most sensitive measure to impurity index. So cross entropy is more sensitive than Gini, and then we're not going to deal with misclassification error rate. Okay, now let's wrap up this relatively long video by going over tree versus linear model, right? So we already discussed this decision trees versus simple linear models in regression analysis. Now let's have the same discussion for the classification. Okay. So on the left, we are looking at linear model. So on the left, these are linear models. And on the right, these are tree-based models. If you look at the decision boundary, so it's straightforward that this decision boundary is linear and this decision boundary is nonlinear. Then the top row is going to be, look at the background color. So here we have green versus yellowish, right? So the background color, it seems that there's a true linear relationship in the top row, right? So if you focus on these top row boxes, there is a true linear relationship. However, at the bottom row, there is true nonlinear relationship. Okay. So what is the takeaway? The takeaway is that if for whatever reason you know that the true relationship in the data is linear, then a linear classifier is going to do a perfect job. So this is going to be the winner. If the true relationship is nonlinear, then a nonlinear classifier, so decision trees are non-parametric, is going to do a better job, right? But the more important question is that, do we have the luxury to see what is the pattern in the data, to visualize it like this? And the answer is no, right? So if the dimension of the data is super large, and let's say we're dealing with thousands of features and we cannot see things easily as this, then we have to try, we can say, okay, let's try both of them and see which one is going to give us a better accuracy, okay? In terms of interpretability between linear models and decision trees, they're both interpretable. Actually, decision trees are even more interpretable. But linear regression models, if we have the assumptions of classical linear models, we can talk about causality as well, right? So what is, for example, what is the marginal effect of changing variables on each other, okay? So this is going to be a separate topic, which